Hi everyone, I'm Ziyun Chen from University of Washington. My talk is about stochastic online correlated selection. This is a joint work with Zhiyi Huang and Enze Sun from University of Hong Kong. My talk will divide it into three parts. The first part is the model online submodular welfare maximization. Second, I'll discuss a new technique developed in recent years called online correlated selection, also goes by OCS. And as the third part, I'll talk about our work stochastic online correlated selection. Let's go to the model part first. Online submodular welfare maximization problem proposed by Kaplanov, Post, and Wonjak is that there are several agents or beings on the left-hand side. Then there will be some items or balls arriving online one by one. We need to immediately allocate it as it comes, like this. Finally, each agent will have a valuation on the set of items he gets. And here, its valuation function should be submodular. Our objective is maximizing welfare, namely the total sum of agents' values. Here we use competitive analysis that our metric for an online algorithm is competitive ratio, the ratio of algorithmic welfare versus the optimal welfare. The classical online bipartite matching problem proposed by Vazirani and Vazirani is actually a special case of online submodular welfare maximization that by taking valuation function VFS equals to indicator of whether there are neighbors in S. Let's see this example that the first ball has two edges to both bin 1 and the first bin and second bin, and say you give it to the second bin, and now the second ball arrives and it only have edge to the second bin, so allocating it gives you no profits and you won't match this edge, which is exactly same to the matching problem. There are several classical algorithms for online bipartite matching. One is the ranking algorithm proposed by Vazirani and Vazirani, which achieves optimal 1:1 ratio in unweighted matching. However, it is hard to generalize to other problems like more general display ads problem which is exactly that the submodule function is maximum of weight of edges, and adverse problem that the valuation function is a budget additive function. However, for the relaxed fractional matching problem, there is a clean algorithm called balance algorithm, achieving optimal 1:1 ratio. And it is much more easier to generalize to other problems and more general submodular function. So a natural idea is considering following combo that's using fractional allocation plus online rounding. This is how the technique of online correlated selection shows up. Consider this relax and round framework. Environment gives both with its incident edges to online algorithm. The algorithm needs to pick an bin for this ball. Now we use OCS to do this picking decision. It receives fractional allocation from online algorithm as input. OCS then rounding this fractional allocation and decides go to which bin. Here, the input of OCS is adversarial input. We formulate online correlated selection problem following. There are n bins, and at each step t, a ball arrives with its fractional allocation vector, where the summation of fractional allocation equals to 1. And the rounding algorithm should put the ball into a bin I with a positive fractional allocation. A cleaner problem is two-way OCS problem. That the inputs satisfy that each ball can only go to 2 bins with one-half fractional allocation. A naive OCS for this is independent random selection that put each ball into a bin uniform randomly. And the guarantee of this OCS is that if a bin is incident to k balls, it is empty with probability 1 over 2 to the k. So can we do better? In the work of Gao et al., they gives optimal two-way OCS. It is that if only one of 2 bins is empty, it puts ball into the empty bin. For both bins are empty, if we still do uniform randomly picking, this will give us no improvement. A question can we think about is that if the bins currently have different degrees, which bin should we go to? And the right intuition is that we should go to the bin with larger degree. So we may tilt the probability towards the bin with larger degree, and actually the optimal algorithm is that doing this very regressively, that always puts the ball into the bin with larger degree deterministically, and if 2 bins with same degree, we just do sample it uniform randomly. The guarantee of this OCS is that if a bin is incident to k balls, it is empty with probability 1 over 2 to the 2 to the k match 1, which gives an exponential improvement compared to the baseline guarantee. I won't go to the proof of it, but there are 2 things to be noticed. The first is that proof is by induction, and the second is that they need to use a negative correlation property, which is only true for two-way OCS. Using this optimal two-way OCS gives an optimal 0.536 two-choice algorithm. Using this OCS technique, previous work has breached one-half barrier for display ads, AdWords, and online matching of reducible resources. And OCS has also been used in breaking 1 over E barrier of non-ID online stochastic matching problem. Now we are ready to move on to our work, stochastic online correlated selection. We consider online stochastic matching problem following, which is proposed by Feldman et al. An instance of online stochastic matching incorporates a bipartite graph G. The left-hand side is offline vertices and the right-hand side is online types, where each type arrives by a Poisson process. Similar to adversarial model, we need to decide how to match each online vertex upon its arrival. Now the competitive ratio becomes expectation of matching size of our algorithm versus the expectation of optimal matching size. The algorithms for online stochastic matching are mostly based on following LP realization, where variables are matching probability of edges. This LP solution serves two rules. The first is the benchmark for competitive analysis. The second and the more crucial one is that it will be reference for online matching decision. Actually, due to the first constraint in linear program, we can directly use it as fractional allocation given to the online rounding algorithm. Now, the framework becomes that stochastic environment provides stochastic instance. Then we solve LP solution of it. Still, we make decision by stochastic OCS. It takes input from LP's fractional solution and round it to decide go to which bin. Here, the input of stochastic OCS is stochastic input. Further, we reduce multi-way rounding into two-way by technique of type decomposition. It will use sampling to decompose fractional solution of each online type into two-way one-half fractional allocation, so that we can only need to design this two-way stochastic OCS. We formulate the stochastic two-way OCS as following. Each type of ball now can be defined by two bins ij it can go to, arrives by a Poisson process with arrival rate lambda ij in time horizon 0 to 1. We define bin i's degree is half of the total arrival rate of its incident balls. Now, a naive OCS is independent random selection that put each ball into a bin uniform randomly. The guarantee of this OCS is that bin I is empty with probability e to the minus di. So, can we do better? We give following the optimal stochastic two-way OCS in our work. If only one of two bins is empty, we definitely put the ball into the empty bin. For both bins are empty, we still tilt our probability towards the bin with higher degree, in a way that the probability is proportional to e to the 2t di. And our guarantee is that bin I is empty at the end with probability e to the minus 2 di times 1 plus di, which is better than the baseline e to the minus di. And actually, this guarantee is tied by the instance that there are two bins and a single type of balls. This optimal stochastic two-way OCS is easy to generalize to non-homogeneous Poisson arrivals. Let me prove this guarantee by induction. Let PIT be the probability that bin I is empty at time t. The derivative of PIT equals to the summation of contribution from ball ij, which is equals to arrival rate of this ball, lambda ij, times the difference of probability that bin I is empty after this ball's arrival and before this ball's arrival. Bin I is empty before this ball's arrival with probability exactly PIT. And bin I is empty after this ball's arrival if and only if ij both are empty at time t and ball ij goes to bin j. So the probability term equals to the probability of both ij are empty at time t and the probability that ball ij goes to bin j, which is exactly the right term. Now we upper bounds the left and right terms respectively. The left term can be upper bound by e to the minus TDI minus TDJ. This is by a weak negative correlated property, which is guaranteed by our OCS, but I will not go to details of this proof. And we using AMGM to the denominator of right term to upper bound it. As you can see, we can cancel out TDJ terms. So, and we further use that the summation of arrival rates lambda ij will equals to 2 times di, and gets the upper bound for derivative equals to di times e to the minus 2t di minus 2 pit. By solving this differential inequality, we get that pit larger than e to the minus 2 tdi times 1 plus tdi. By taking t equals to 1, we get the upper bounds we need. By applying two-way stochastic OCS, we get following great result. For unweighted and vertex-weighted matching problems, we directly use the optimal two-way stochastic OCS I just introduced. With analysis opening the black box of this optimal two-way OCS, we get improved ratios for non-IED model and query commit model. By designing different two-way stochastic OCS for specific problems, we break 1-1/E barrier for the first time for problems stochastic adds and stochastic AdWords, where the later one is a decade-old open problem proposed by Maheta in his survey. Let me summarize the talk by future direction. The general unlicensed submodular welfare maximization problem. In the work of Kaprilov, Post, and Wonjak, they show that polytime algorithms are, at best, one-half competitive in adversarial model and 1-1/E competitive in stochastic model. They consider a special class of submodular function called coverage functions to give this hardness. However, these upper bounds are relying on computational hardness of max coverage. Another good news is that there is an 1-1/E competitive fractional algorithm for coverage functions. So a natural question is that whether there is any stochastic or non-stochastic OCS for coverage functions so that we can beat above upper bounds. That's all. Thank you.